All right, this is lab 1 for physics 2211 about constant velocity. So the purpose of this experiment was to observe the motion of an object moving at a uniform speed in a straight line. I personally used a candle rolling across a granite countertop. The models that were used in this analysis was a video analysis software called Tracker that allowed me to track an object's position over time accurately by pinpointing the position at different timestamps. And then the computational simulation tool, GlowScript, using Python allowed us to input the initial conditions like the object's mass and the object's initial position and velocity in order to then create a computed model of the velocity and the position versus time graphs, assuming that the object's velocity was constant and there were no outside forces acting on it past the initial force of motion. The principles used here are the Newton's second law of motion / the momentum principle and the result. Again, there were discrepancies between the two models, but we are going to talk about the considerations of different experimental errors or outside physical forces acting on it that would cause those discrepancies. So this was a demonstration of the Kindle rolling across the countertop. Again, you can see the system here is the Parks and Rec Kindle, and the surroundings is the hand that was the initial source of motion, and the granite countertop as well as the earth. This is the observed motion graph points as well as the graphs generated from it. These are the points I collected of the X and Y coordinate positions along with every single timestamp. This is when the observation start time was, and then the last time of the observation. The initial position recorded here, as you can see at the first timestamp, and the initial velocity vector was calculated using the change in position over change in time formula with the first few initial points. Again, you can see the graph follows a linear trend, although it is not perfectly linear, and we're going to talk about why that might be at a later slide, although it is technically supposed to follow a linear trend because the velocity is constant. So this is the computational model using GlowScript. You can see I input the initial mass as well as the initial position and velocity vectors for the candle. The time here in the while loop is doesn't go above the last recorded time of the data that I recorded, and then these are the velocity update and position update formulas. We calculate the velocity every time by taking the last recorded velocity and adding the acceleration times time to it, as well as for position, taking last recorded position and adding velocity times time to it. Acceleration here is equal to the net force divided by the mass, because by the second law of motion, force equals mass times acceleration. Therefore, the acceleration is going to have to equal the force divided by the ball's or the candle's mass in this case. These are the graphs that were derived from this computational model. Again, the initial conditions were inputted and the computer calculated what the position versus time and the velocity versus time graphs would be, assuming that the velocity is constant and assuming that there are no forces acting on it. That is not exactly what happened, as we saw on the previous slide in our observed motion. So again, going over the Newton's second law of motion or the momentum principle, the net force is equal to change in the rate of change in momentum, and that is equal to the rate of change in mass times velocity. Since momentum is equal to mass times velocity, that can be equated to mass times the rate of change in velocity, and because the rate of change in velocity is equal to acceleration, in this case we can substitute the acceleration here and we get net force is equal to mass times acceleration. Because velocity in this case is assumed to be constant, that means acceleration. The rate of change in velocity is 0, that means the acceleration is 0, and anything multiplied by 0, so no matter what mass the candle was, is going to lead to 0, which means that there are 0 net forces acting on the candle, assuming that it was moving at a constant velocity. Again, the graph of the observed motion wasn't identical to the computational model, although the computational model was built on the observed data. And the reasons for this could be some data entry errors on my part when I was mapping the positions at every single timestamp. It could be model idealization because we are assuming that there is no friction, no air resistance, no any forces like that could be present on Earth. It could be surface irregularities of the countertop. It could be slanted or rough surface, some friction present. The camera angle and perspective could also have led to some data entry errors because it would have been harder to map accurate positions if the angle was inappropriate. What if there was friction air resistance? That would lead to varying velocities, that would lead to net forces acting on the candle, and therefore the acceleration would be non-zero and there would be net forces acting on the candle, which would lead to the varying velocities, which is why the graph could have been the way it was for the observed motion. So again, despite the discrepancies between our two models, the computational model did provide a useful approximation for the object's motion, underscoring the importance of considering both idealized and real-world conditions when analyzing physical systems. Future work in these experiments could benefit from refining the model to account for these external factors and improving experimental precision as well to enhance the alignment between theory and practice.